6.4, number 27. We're given triangle ABC. We're told that angle B is 55 degrees and the length of side B is 11.2. And we're told to solve triangle ABC. That means to solve a triangle, figure out the lengths, the measures of every single side and angle. So we're going to need angle A. We know angle C. We're going to need little a and little c. Three things. Angle A is the easiest. 180 degrees is equal to 90. Angle C plus 55. Angle B plus A. So A is equal to 35 degrees. Hooray. I'm going to write that down, make a note of it. Could be important. Next, let's see here. Let's take a look at the sine of B. This could be interesting. Sine of angle B is little b over c. So the sine of 55 degrees is equal to 11.2 divided by c. A little bit of algebra will give us that little c is equal to 11.2 divided by the sine of 55 degrees. Okay, so how are we going to find this sine? Well, we can fire up our calculator, fire up the internet. There's a scientific calculator built into Google. I'm going to go ahead and just take this calculator here. Punch out in 55, make sure it's set to degrees, not radians or gradients. Take the sine, I get 0.8, oh, big mess, that's okay. The important thing is this, 0 point, it's less than 1. Yeah, if you're doing trigs with sines and cosines, they better be less than 1. They better be between 1 and negative 1 inclusive. Tangent goes from negative infinity to positive infinity, but your sine and your cosine better be between the two. And oops, we're going to take 11.2. We'll just divide it by that 8.19 or 0.819. Oops. 0.819. We'll get 13.67. All right. Cool, so we found one of the angles. C is 13.67. Go ahead, we'll write that down. All that's left is to find side B. So, let's see here. We could either use the Pythagorean theorem, but this isn't really a Pythagorean theorem section. So, let's go for cosine of B. Cosine of B is equal to A over C. So the cosine of 55 degrees is equal to A divided by C, which we found to be 13.67. So A is equal to cosine of 55 degrees times 13.67. Let's see what that is. It's going to be 55 cos times 13.67. Hooray. I get 7.84. A little trouble with the other switching there. 7.84 units. So if we wanted to really overdo this on the trig functions, we could take a look at the cosine of angle A. Alright. Cosine of angle A would be 7.84. We'll write that down. So this triangle has been solved, but I want to look at solving A a different way. Cosine of A is the opposite, 7.84. or excuse me, the adjacent 11.2 divided by the hypotenuse 13.67. Let's set that up. Do 11.2 divided by 13.67. All right. So I know what the result is, but I don't know the angle. Remember, the idea behind cosine, sines, all these trig functions is that, one angle in a right triangle, it's similar. All of those 90-degree and 25 triangles, they're all similar. 45, 45, 90 triangles, all similar. 30, 60, 90 triangles, all similar. So you give me one length, I can compute them. But it works the other way too. You tell me the ratio between those sides, I can tell you the angle. Now, this isn't strictly an inverse. It's not. I'm sorry. It's not an inverse function. Because cosines, sines and all of that, they allow degrees to be more than 360. Or 90 or 80, whatever. Punch in the sine of 540, I get an answer. 0. Yeah, that is the sine. 500 degrees, cosine. I get an answer. It's negative, but it's still a cosine. So that means if I punch in a trig function or a ratio, there's more than one angle that corresponds to it. However, you can compute them. You can compute and you can find all the infinite number of angles. So instead of a inverse cosine, which it kind of is, but not really, common abbreviation is ARC for arccos. And this turns out to be 34.98 degrees, which is pretty well within error. We're off by 2/100ths from the value that we found through addition. So I think that's a rounding error right there. So this works too, using an inverse trig function, the arccos. On this calculator, this button, the INV, this is just Windows calculator that's been going on for forever. This gets me my inverse functions. So what I'm going to do is I'm going to punch in 11.2 divided by 13.67, enter, inverse cosine 34.98. Note that it is not these, sinh, cosh, and tanh. Those are not inverses. These are hyperbolic functions. Similar to trig functions, but a little different. All right. That's number 27. Next problem. We're looking at number 48, section 6.4. If A and B are acute angles in a right triangle, then sine of A is equal to cosine of B. Okay. Well, let's draw a picture. So we'll just draw a picture and label things so that everybody's on the same page. Let a little crummy right triangle here, but it doesn't have to be perfect. A, B, C, A, that's a little C, B. Alright, so if this is the case, if things are labeled like this, then the sine of A is opposite over hypotenuse. And let's see here, the cosine of B is opposite, or excuse me, adjacent over hypotenuse. I don't know why I keep messing up those cosines. Sine of A, cosine of B. Easy enough to prove. Next problem. Number 54 in section 6.4. Okay, in these problems, they start talking about the three other trig functions that are related to sine, cosine, and tangent. They are related to, but distinct from sine, cosine, and tangent. Sine, cosine, and tangent. but you can pretty much treat them the same. It's cosecant, secant, and cotangent. So SEC, COT, CSC. This right here, this proposition that we're setting out to prove, is actually one of the ways that you can define the cosecant. You could define the cosecant function to be 1 over the sine function. Likewise, I could define secant to be 1 over the cosine. So secant of A would be 1 over cos A, and cotangent of A would be 1 over tan A. How the book defines it, though, is given our poorly drawn triangle here, cosecant of A is C over A, hypotenuse over opposite, by definition. Well, the sine is defined to be opposite over hypotenuse. 1 over the sine of A is 1 over A over C is actually C over A, which is cosecant of A. And we're done. These three functions, cosecant, cotangent, secant, they're useful for doing things called trig identities, where you want to figure out what a trig function is in terms of another trig function. Like if you actually just do a phase shift, it's called, on a sine and a cosine, they're the same. You take the cosine of an angle, you add 90 degrees to that, that's the same as the sine of the angle. These are useful for things like that, or if the cosine of A is blah, what's the cosine of A divided by 2? Those are useful trig functions to know. But these are especially useful in calculus. The derivative of the tangent is the secant squared. That's way outside of this class, but that's one of the reasons why these guys come up. Another trig function, trig identity, really important one, is that if you take the sine squared of some angle, you add it to the cosine squared of the same angle, you get 1. Really cool. Really, really cool. This is theorem 6.14 in the textbook, and can be shown using the Pythagorean theorem. Theorem 6.13 or 6.13 is another interesting identity. The tangent of an angle is equal to the ratio of the sine of the angle to the cosine of the angle. It's another interesting trig identity there. Let's move on to our next problem, though.